Hi, I'm Darren and welcome to Level Up EE Lab. Well, I finished the repairs on the EUW-15 power supply and it's working. Sort of. Let's check it out. I decided not to remove the 4 original big filter caps. Instead, I'm going to bypass them with radial style replacements under the chassis. I will, however, remove these 2 axials and replace them with radials. Axials are just getting harder to find and they typically are more expensive. But to package these radials robustly, I decided to make 2 simple printed circuit boards to hold them. Because the boards are so simple and don't have tightly spaced components, I can use the super fast Sharpie method. It starts with a layout drawn to scale, of course, and you can use the printed layout as a template to mark the center holes in the PC board. Here I'm using a simple center punch to mark all of the hole locations, including the mounting holes. Myself, I prefer to drill all the holes as the next step, but it's up to you. You can drill them after etching if you want. Next, use a fine point Sharpie to mark up the board. I did scuff the board beforehand to remove the surface oxidation, so that helps the Sharpie ink stick better. You can be much more graceful and organic with the trace routing. There's no need for straight lines and right angles. I typically connect all the points first and then fill in the areas second. Don't be bashful with laying on the ink. The more area you cover, the less copper has to be etched and the longer your jug of etchant will last. If you make a mistake, fixing it is easy. Just use a cotton swab dipped in a bit of acetone as an eraser. Now, decades ago, I used to make boards at home this way all the time. In fact, I remember that Radio Shack used to sell markers just for this purpose, but in hindsight, they may have just been rebranded Sharpies. Here's what a finished board looks like after tin plating. Now notice that there is some unevenness in the copper. That's because the Sharpie ink isn't uniform. But it's just a cosmetic issue. There's still plenty of copper in the traces. For mounting the boards to the power supply chassis, I'm going to harvest a few mounting lugs from these old terminal strips. These lugs are already the correct size. All I need to do is drill them out of the Bakelite and attach them to my PC boards using some number 6 hardware. Alright, here we go. I have finished the mechanical repairs on the EUW-15. Let me walk you through them, starting with looking at the bottom of the chassis first. Most obvious are the 2 printed circuit boards that I put in. This is the one that's containing the replacements for C1, C2, C3A, C3B. That's the 4 big monsters. Now I did leave those in place so that looks the same when I put this back over on the top side, so cosmetics still are fine, they're not affected. This board here contains the replacements for C4, C5, and C8, and I also moved R1, which was here and now is on the board, and then a single diode here replacing the 2 big selenium rectifiers, D5 and D6, which you can see over there, upper left hand corner. Don't need those anymore, and this is actually overrated. It's a MUR 180E, I think it was, so it's 800 volts peak inverse voltage rating. It's a fast switching diode. Don't really need all those, but nonetheless, you build with what you got in your junk box sometimes, even if it is a bit overkill. And that's kind of what I did here. Let me rotate this around. Sorry for bumping the camera there a bit. Let me see if I can move this actually in the view a bit better. So the 4 diodes, I replaced those with the most common 1N4007s. Yes, I don't really need 1 kilovolt peak inverse voltage here, but I don't stock all umpteen different varieties of power supply diodes. And 1N4007s are so widely used, and I buy those dozens at a time, so no issue with putting them in the circuit here. The one thing I did come up with, though, is better strain relief, and let me flex this so we can see this a bit. So when you swap out these jumper wires, which I've temporarily removed, these terminal strips are not well supported and you can actually flex these a bit. Now, just connecting these point to point here is going to create a problem. I thought if you started to stretch these, you could put tensile stresses on those diodes, and that's not good. You might accidentally pull the lead out of the case. So I fixed that by just making the diodes like a little cone hanger. So that took care of that. I think the last comment I would make here on the new things I added was this purple wire. So anytime I'm putting in new connections where there's more than a couple hundred volts, I use this Teflon insulated wire. It's rated for 600 volts just to have a little extra insurance for voltage rating. Now, that's probably, again, another item that's overkill, because what about the rest of this wiring? Is it really up to 600 volts? Probably not. But if I'm going to put in replacement wire, I'm going to put in some good stuff, and I happen to have, I don't know, a few dozen feet of that laying around, so I went ahead and used that. Last thing I would comment on is on these older rigs, whenever I change out these caps, whether they're electrolytic or film, I do test them afterwards. And here is the tester. I've shown this in some of my prior episodes. It's my very crudely assembled, ugly construction version of Mr. Carlson's capacitor leakage tester. So definitely recommend, if you're working on older gear, go check out his channel and see how he designed that. And he makes those details available on his Patreon channel. And just for interest, in this case, I wanted to see, were all these caps bad? And there's a total of 10 of them, I believe, in here. No, I'm sorry, there are 9. And I checked them all, and only one of them is good by the standards of that tester. Good meaning it goes through and lights up the green light at a total amount of time similar to a new capacitor. So it means it has, leakage that's similar to a new capacitor. Only C6, that's the .01 film cap, checked out good. All the rest of them were horrible. So confirmed what was probably an obvious expectation, that the caps were just beyond their lifetime. And now there are new ones in here, so all good to go. So what I'll do next, I'll turn this over so we can take a look at the top side of the chassis. And this is the top of the chassis. So a few things to talk about. First, here are the 4 big filter caps. As I mentioned, I did not replace those. They're still there for appearance only. They're not electrically connected. Actual repairs I had to make on the top side include the divider resistor bank. That was the spot over here where it had that cobbled in extra resistor that I can't understand why it was there. Nonetheless, the 5 resistors checked out fine, so I reconnected them per the factory schematic, so that should be good to go. I did fix this selector switch. This is the switch that controls whether you use the divider network or use the regulator. And this was a bit of a challenge. I mentioned in the prior video that I can apply heat and usually free those up. So it turns out you can use a standard Weller soldering iron, in this case an SPG 40, take the tip off, and you can put that right onto the metal shaft. Now, of course, I take the switch out of the front panel, so I'm not risking scorching and burning the front panel, but that's a controlled way to apply some heat. That did get it freed up, but it didn't stay unstuck. Typically, when there's corrosion in there, that's enough to get it freed up, and I can put some lube in there, a little bit of additional solvent to get it to stay free. Wasn't going to stay free. I had no choice to take it apart, and these things are always dicey to disassemble, but I was able to get it apart, and it turned out it was just the grease that dried up, and what was left behind looked a lot like dried up old plumber's putty, which, if you think about, most greases are oils with some sort of filler, and a lot of times that filler is just clay. So that's what was binding it up. Cleaned it off, put some fresh grease in there, and it's working fine now. No big deal. Front panel, let's talk about that briefly. On a lot of these old radios and pieces of test equipment, I will put a light coat of just regular automotive car wax on. I decided not to on this one. The main reason is there was already some blotchiness and unevenness on the panel, and I've noticed in the past that wax sometimes makes that look worse, meaning some areas will get even shinier and not blend in as well. So I decided, in this case, don't do anything for the front panel. I just left it alone. Now, where I did try to clean up a bit of some of the old patina, if you will, was on the chassis. You can probably see in the video here that there are fingerprints on here, and these are not dirt. These are actual spots of corrosion. There is a chemical reaction that happens from skin oil, sometimes from fingerprints over the years, and it actually reacts. It's a corrosive type reaction with the plating on the chassis, and they're almost permanent at this point. They don't come off with detergent. However, I did take a little bit of WD-40 on a few pieces of paper towel and went over lightly. That cleaned up a lot of the other grime that the detergent method didn't take off. So there must have been some further oxidation or corrosion on there. It still looks a little blotchy. I mean, this is not, factory condition by any means, but, for something this old, it doesn't look too bad at all. And the last thing was I was able to get the transformer, it's not perfectly vertical, but I was able to carefully bend the tabs and get it back close to where it should be. There's actually some permanent deformation to the chassis itself where this mounting hole in particular got pulled up a little bit. To really fix it, I'd have to take the transformer off, take all the stuff off the bottom of the chassis, and take it over to the, anvil basically, or something to, metal to pound it out on. Not worth that much tear up. It got to 87, 88 degrees of vertical, so it's good to go. So what's next? Well, I'm going to put those jumper wires back on, get the configuration set that I want, and then power this up using my dim bulb tester. At this point in the episode, I had plans to narrate over a high-speed clip of me installing these jumpers, but I kept sticking the back of my head in the frame, and nobody needs to see that. So I trimmed the clip down to just these few unobstructed bits. The purpose of these jumpers is to allow a student to reconfigure the AC to DC conversion stage to build various architectures, things like full wave rectification, half wave rectification, add or remove various filter caps, and so on. The Malmstadt book that I mentioned in the first episode does show a lot of detail of how to do this and what the behavior of each circuit configuration would be. But outside of a learning lab environment, having this level of complexity in a power supply is not very useful. In fact, I debated dumping this entire feature and just hardwiring the circuit the way that I wanted. But as it turns out, installing these jumpers is actually pretty easy, and in the end, I used them to wire up the default voltage doubler configuration. Alright, here we go. I have the power supply connected up to my trusty dim bulb tester. I won't go into great details what this is if you're not familiar with it. I do have a separate episode of how I built this and what it does, but just in a nutshell, it lets me apply a controlled amount of voltage and have a visual indicator by using this incandescent light bulb if this is drawing too much current. So for the first test, what I'm going to do is set the AC on, set the high voltage output on. I have my multimeter connected up to the output, and I have set the selector switch to divider. I'm going to put this at, say, in mid-range. And what I'm going to look for, first of all, is that bulb does not glow brightly, and see if I actually get some high voltage coming out of the power supply. And also, of course, make sure the tubes are glowing brightly. So, in the words of Ray Arnold, hold on to your butts.
This item contains hazardous voltage and safety precautions must be followed. If you're following along and working on your own version, you're doing so at your own risk.
So I'll start bringing the AC voltage up. Starting to get a little glow out of the bulb. That's okay, that's normal. Getting up to about 90 volts or so here now. I think I can see the filaments glowing in the vacuum tubes. That's also a good sign. The panel indicators are both coming on, and of course, 212 volts on the meter. So that part seems to be working fine. May not be fully in range because I've got lower voltage here and voltage drop, of course, through the light bulb, but that seems to be believable value, so that's working well. Okay, so I'm going to reset this, and then the next test I'm going to do is going to be looking at the regulator circuit and see if I get regulated voltage coming out. So I'll power all this down and restart. All right, everything is off. I'm going to move the divider regulator switch to regulator, turn on the power switch, turn on the high voltage output, and I've reset the control here for the rheostat back to 0, of course, and turn on the power here. And start bringing up the voltage. Again, I don't want to see that dim bulb glowing brightly, but I do want to see a regulated voltage starting to show up here. Now I've set the range control to roughly mid-range, so I'd expect something between 250, 300, 350, somewhere around there. So let's see what it gets to as I start cranking up the AC voltage. The bulb is glowing dimly. That's a good sign. I see the filaments glowing again in the vacuum tubes. That's another good sign. Now I am a little low here on voltage, and of course there's some voltage drop from the bulb adding to that. So nevertheless, let's see what's happening here. Now that's a concern. That number should be changing as I'm altering the regulator voltage setting. So I may not have enough supply voltage to the power supply. So because the dim bulb hasn't reacted alarmingly bright, I'm going to turn this down and then flip this switch, which will bypass the bulb and put full voltage from the rheostat onto the power supply. We can see that come up a bit. I'm going to move this up to about 115 for full line voltage now on the power supply. And okay, that is not working correctly. That number should be changing as I'm adjusting the regulator voltage. So, all right, I'm going to have to power this down and take a look at, I guess, all the mods I made and the rest of the circuitry and figure out what's going on here. Okay, I have found and fixed the issue, kind of cutting to the chase here, but just to show real quick that it is working. And you can see I can adjust the regulated voltage up and down, and it tends to be pretty stable and stay put. Now I'm going to shut it off now, and I'll explain why. I just did a quick test there. So on my videos, I typically don't document every single step in troubleshooting. Quite frankly, that just gets boring, and who knows how long troubleshooting is going to take. So just cut to the chase is typically what I do, but then go back over the steps that I did and kind of interleave some video that I recorded during the troubleshooting and just make it more concise and kind of get to the points. So diving right in, the first thing I did was check the jumper wires that I put on to make sure I did get the pattern correct, and they checked out fine. I looked at my new printed circuit boards for any errors or any wiring errors that I might have made when I hooked up everything. No issues there. So then the next thing to do, Heathkit has been very good over the years with putting on their schematics, and I'll show on screen here voltages at various nodes, and they also tell you what conditions to check those voltages at. That's extremely helpful when you're trying to at least box in where the problem might be. So I did that, and everything checked out okay, except for the voltage for the 6L6 screen grid. That's supposed to be 560 volts, but I was only seeing around 320-ish, and it was not stable. It was dropping steadily as the power supply was on. That's a classic sign that something's running hot, resistance is going up and causing voltages to drop, or even more alarming, maybe a load is changing and drawing more current. So that was definitely alarming, so shut it off, look at the circuit more closely in that area. Now, I did find that I was probably a little too overlooked and a little anxious in my, I guess, troubleshooting of the initial condition of the resistors in the power supply, and R1, and I'll show on the schematic here, that's supposed to be 3.3K, actually was out of spec around 5.2K, and then the two 15K resistors, R2 and R3, were also about 10%, oh, actually a little bit over 10% high, like 15% high. So no issue replacing those. Figured, well, what do I got to lose? Swap those out with brand new values, no change. So what's left to look at? I knew the problem was in that portion of the circuit, so it narrowed it down to just the 6L6 GC tube. There's nothing else that should be drawing any current from that part of the power supply. It's just the screen grid voltage. Now, I mentioned in the first video on this episode that I did check that tube fine on my TC162, I think it is, Sencor tube tester. No issue there. There's always a caveat, though. That's not a full performance tube tester, and for pentodes, it just tests them like diodes, and I think triodes, it tests them like diodes. So you're not going to see intergrid leakage, you're not going to see conductance and blah, 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 and all that other good stuff. It's just a quick test. And as always, the caveat is the circuit you're using the tube in is the final judge on it. And as it turns out, that was the problem. The 6L6GC rather had some sort of internal malfunction. Now, the prior owner could have overheated it, and there could have been too much conductance from the screen grid to the control grid, or who knows, but the simplest thing to do was just swap out the tube. And unfortunately, I didn't have a GC version in my stash, but I did have a 6L6. Now, I'll show those on screen so you can see the difference. The 6L6 was the original form, and the GC, the G stands for glass, of course, and C is revision C. They're not directly interchangeable with each other. You can take the newer one, the GC, and put it in place of just the 6L6, but you're not really... it's not really wise, I should say, to replace them the other way around. The reason being the 6L6 is only rated at 19 watts plate dissipation versus the 6L6GC at 30 watts. And also, the 6L6 has a lower specified maximum plate voltage of 360 volts versus 500 for the 6L6GC. Didn't stop me. Figured, what the heck, I'll try it anyway, at least try it briefly. That's what I've got in the power supply, and if your eyes were keen, you'd see it right here. That's the top of the tube sticking up right there, and it works. So I only had it on for a few seconds just to show that, yes, that was the issue. Yes, it was a problem with the 6L6GC tube. So the permanent fix is I have ordered a new tube, and unfortunately I don't have it in time for this video. Probably won't have it for another 10 days or so, but whatever. I at least can show maybe a follow-up epilogue in the future when I button this all up, but it's working. I did purchase, I've never done this before, a JJ electronic tube, so technically that's a brand new tube. Those are made in Slovakia, I think, and they're not cheap. Even a singlet is about 25 bucks, but I understand that they're very popular with folks who are maintaining guitar amps, audio amps. They're typically sold in matched pairs or matched quads or whatever your amp may need. But in my case, I didn't need any matching. I only needed one tube. So in the future, I will do a little quick follow-up to show putting that JJ electronic tube in here and then finishing all the performance measurements. It certainly was disappointing that, except for one little tube malfunction, I could have had this power supply repair done in 2 videos, but that's how it goes sometimes. Now, in the third and hopefully the final episode on this power supply project, I will have that new tube and be able to put it in place and try out the power supply and make those measurements and show that it works. Now, with this added delay, there is a little bonus that I'll have for the final episode, and that is I figured out how to do LT spice simulations on circuits that use vacuum tubes. Kind of interesting to see. So I will have some simulations to show along with the power supply working with that new tube. So until next time, bye for now.